All right, so this is the second day on logarithmic functions, and today we're going to be solving logarithmic equations, and then we're also going to use the change of base formula to rewrite with a different base. So about halfway down on the second page, it says sometimes you must use logarithms to solve exponential equations, but sometimes you don't have to. So if you can, you want to write each side of the equation with the same base and then set the exponents equal. So on example 5a, that's exactly what we can do. So we can rewrite the right side of this equation as e to the negative fifth. So 1 over e to the fifth is the same as e to the negative fifth. And then if these are the same base and these two sides equal each other, the only way for that to happen is if the exponents equal each other. All right. So we would solve that, and x is going to be negative 3. All right, so if we look at b, and we think, can we rewrite these each side with the same base? You can't. So there's not like a normal type of exponent that you can raise. You can rewrite the base and it'd be the same on both sides. So like 4 to some power could be 5 without some kind of weird decimal or fraction. So this one we are going to have to use logarithms, and we're going to use the exponential property of logarithms, which is if we have log base b of a to the r. So the logarithm of something raised to a power, we can take that power and bring it down in the front and make it r times log base b of a. So you might wonder why that's important. Well, it's important because on exponential equations, your x is up at an exponent. So we have to have a way to get that exponent down, and that is by using logarithms. All right. So if you cannot write the equation with the same base, what we're going to do is isolate the exponential expression. All right, so that's just using addition or subtraction, division, or whatever to get the exponential expression alone. Then you're going to take the natural log of both sides. All right, and then the whole purpose of doing that is so now we can use that exponential property to bring the exponent down. All right. And once the exponent is down, then we can solve for it just using algebra. Okay, so let's look at b. All right, so the exponential expression is 4 raised to the x plus 7. So it is already isolated. So we're ready to take the natural log of each side. So we just write ln in front of the 4 and ln in front of the 5. All right. So the whole purpose of doing that is so now I can bring that exponent down. Now, because our exponent had multiple terms, we do want to write it in parentheses. Okay? And there's different things you can do, but the quickest way to solve this now is to go ahead and divide by the natural log of 4. So then we're just left with x plus 7 is equal to the natural log of 5 over the natural log of 4. And then lastly, we just subtract that 7. And that's the answer. Now, I have a bunch of examples because they're all just a little bit different. So on the next page, we're going to solve this one for x. So this time our exponential expression is e to the x. So we have some work to do to get that by itself. Okay. So once we get the e to the x alone, we're ready to take the natural log of each side. Now, this one is a little different because we can use the inverse properties on this one. The natural log of e to the x is just x. And so we have our equation solved. So that was a property we talked about in the previous lesson, because logarithms and exponential functions are inverses of each other. They undo each other. And so you are just left with the x there. All right. So on this one, we would need to divide by 4 first to get e to the x alone. All right. And then there's no way we can write 12 as 3 to some power, like some integer power. So we would take the natural log of each side. All right. And don't forget, the purpose of that is so you can bring the exponent down. And once it's on the normal level of the equation, we can solve for it just using algebra. So all we need to do on this one is divide by the natural log of 3. Okay, so that is it. Now, I know it's really tempting to try and reduce the 12 over the 3, but you can't. If that's it, that's all you can do. All right, so in class, I had the students do this one on their own. So if you want to pause the video and then work it out and then start it back and check yourself, you can. But I'm not going to talk through this one. I'm just going to do it. Okay. So this next one has kind of got a lot going on. Like it's the same steps. It's just kind of weird at the end. So to isolate, we would want to go ahead and add that 1. I'm sorry, subtract that 1. And then we would need to do the natural log. Right, and then we bring down the exponent because that's the whole reason why we did the logarithm. All right, and then we'll go ahead and divide. Okay, so this one ends up being kind of a mess for our answer. Oh, that's a 4. Sorry. Yeah. Okay, now G is one of the more difficult ones because there are exponents and variables on both sides. We can't write these with the same base. So we would go ahead and take the natural log of each side and bring our exponents down in the front. Okay, so this one is different than the previous ones because we want to solve this for x, and we have x's on both sides. And so instead of what we have been doing, which is dividing by like the natural log of 3, we're actually going to need to distribute it on this one. And when you multiply the natural log of 3 by something, it's just multiplied in the front. So like if this had been 4 here, that 4 would just go there. Okay. Now, just like normal equations, there's x's on both sides. We need to get the x's on the same side. And to be able to solve for x, we kind of have to pull it away from the other parts, which involves factoring out the x. And then we're ready to divide by what's being multiplied by the x, and we'll be done. Right, and we can't simplify this. Like these two can't be reduced because that minus sign messes that up. So this is it. This is the answer. And then the last thing we're going to talk about today is the change of base formula. Now, it used to be really important because we would use calculators in this class, and they didn't have a lot of the features they currently have. So I didn't teach it for a long time, but then I saw an ACT question that involved using the change of base formula. So I decided I would start teaching again, just so you guys can get one more question right on the ACT. It's worth it. All right, so if we have log base b of a and we want to write it with a different base, like c, the numerator would be log base c, or whatever base you want it to change to, of the argument a, over log base c, whatever base you want to change to, has to be the same on the top and bottom, and then over log base c of the old base. Okay. So in the past, what we would want to do would change it to like common log or the natural log. The log buttons are easy to get to in the calculator. So that's what we're going to do on example 6. So log base b of m, if we want to change to common logs, that's log base 10, or log without the base written. It'll just be log of m over log of the base. For natural logs, natural log of m over natural log of b. All right. So for log base 2 of 7, we want to change that to common logs. It's just going to be log of 7 over log of 2, or natural log of 7 over natural log of 2. Okay. So your assignment is also in this packet. This number, if it hasn't already been changed on your sheet on number 12, I want you to change that 11 to a 10, please.